Okay, let's start today's hep-ph seminar. Today's speaker is Professor Werner Porod from University of Wurzburg. He'll talk about LHC bounds on composite Higgs models, implication for naturalness. Please start if you're ready.
Thanks for the invitation. It's a pleasure to be here. Concerning the title, I will actually focus mainly on LHC bounds and only come to the very end towards implication or potential implications for naturalness. Okay. So I will briefly talk about motivations for composite Higgs models, as I've included some basic features about composite Higgs models, as I was unsure whether everyone knows about the composite Higgs models. So if everybody tells me you all know this, then I will be faster, but I can also be somewhat slower. And then I will talk about models beyond the minimal one, because the minimal models has a very specific features which are not very general. And we expect actually in a more complete model featuring ultraviolet completions to have additional features. And I want those to be explored and see what we can learn. And then I will come really to the LHC terminology. I will first discuss those in terms of simplified models. And then I will take out a very specific one, which is well motivated, and see how we can apply the features that we learn here to this particular model. Just to see how this tool of simplified models are useful for exploring sequence of models, so to speak, because we as theoreticians, we know how to construct models, we have many ideas, but of course we can have only one realized in nature. So just very briefly, the standard model Higgs, its web gives rise, so we parameterize these fields in this term here for the SO2 structure. The neutral component gets a vacuum expectation value, and this guy is responsible for the breaking of the SO2 times U1 subgroup to U1 electromagnetic. It gives masses to the vector bosons, to the fermions, and of course, then we have one scalar predicted, and its properties are very similar to the ones that we have discovered at the LHC. So everybody speaks of this scalar as the Higgs boson, but to be precise, we don't know yet. Just to give an idea of what do we know, here are some results concerning a different decay trend of this Higgs. So it's assumed here that it's produced as the pure fusion to Higgs, and then this goes to, for example, Z, where Z means one of the Z bosons is off shell, the second one is on shell. And you compare this here to different ratios, and this gives here what's the production channel versus the blue channel. And sorry, the closer this is to 1, okay, there's some theory calculations involved in addition. So in a perfect way, everything will be to 1. And then we have here the 1 and 2 sigma deviations. And here as well, for the other slightly differently. Important point here is these are mainly couplings to the vector bosons, to the photons, and to the third generation fermions. So those we know well. We see within let's say 20–30% disagrees with the standard model prediction. But the important point for later on is they do not involve any Higgs self-coupling. So for example, what Han has presented before, the 3 coupling, we don't know. So we don't know what the potential looks like. That's the important thing. So we do not really know the Higgs is the Higgs of the standard model as long as we don't have this potential. And this, as you have seen, will be very difficult to measure. And from the theory side, there's this phenomena of fine-tuning under quotes naturalness, because quantum corrections, roughly speaking, have the structure that we have here, corrections to the vacuum expectation value squared over its value. In this case, roughly speaking, like the mass of the heavy scale, either the mass of the new particles, it could be related to flavor groups, to grand unified groups, could be even gravity, so it would be the Planck scale. You have a coupling here squared, which is order 1 typically. It can be smaller, it can be slightly larger. If you transfer to base, it should not be much larger. But the important point is that is like the ratio of the mass squared over the Wef squared. We know the Wef is ordered to only 50 GeV. As soon as we have something here 10 to the 4, 10 to the 5, we have corrections which are the order of the Higgs mass itself. And this, we don't know, we would really have to fine tune having different signs. Of course, there could be symmetries like supersymmetry. Then we would have relations between masses and couplings, and then those would cancel because of symmetry reasons. Another way, and that's what I will focus on, is the case that you will have a kind of bound state in the pseudo-Goldstone bosons. By the way, those pictures I got kindly from Thomas, so thank you very much for that. Well, we have a stage group that, as you know, standard model SS3 color, SS2 left, U1. If we just take one generation of quarks, then we have what happens global symmetry, SS2 left, is statistically small to distinguish it from the SS2 left, which is gauge here, because there's the global symmetry, times the SS2R here, which would be a symmetry between those two guys, because the gauge interactions do not care whether it's an up quark or down quark. And we know at this very small scale, we have the condensation of this combination of a left-handed with a right-handed quark, and this breaks this product group down to a diagonal form, giving rise to 3 pseudo-Goldstone bosons, limited pions. And this is the very same idea that we use in the composite Higgs approach. So I'll first present the minimal one and then come to features which go beyond the minimal one. Just to give you the general framework, we have here the global symmetry of the strong sector. We assume there's an additional gauge group, could be SU4, for example, or any other gauge group you like. Even things like SP4 are considered. You have a kind of condensation here as well, potentially even 2, one for the electroweak, one for the strong sector. Then this will leave out of this group G a subgroup H1. We know what the standard model gauge symmetry group looks like. And of course, this can be inside the H1, but strictly speaking, it need not to be inside. And then you would have the ungrouped group H, which in our case would be electromagnetic distance times the SS3 color. And of course, the question is, what are the groups, what are the smallest groups which we can use in this approach? The minimal one, it turns out, which gives you just one Higgs doublet with respect, well, it's a beta with respect to SE2 left and SE2R. Sorry, here now I'm using the large letters again, but this is not the gauged one at this stage yet. It will be gauged eventually, but at this stage it's really a global group. So you start with a global group SO5 over U1x. U1x you need to give hypercharges to all the standard model fermions. This gets broken down by a condensation to the SU4 times U1x. An important thing is that the SU4 is at least locally equivalent to SU2 left times SU2 right. And that's the symmetry group we would like to have to be consistent with electroweak precision data. It's not really required, but that not every group will lead to this, but that's what we require from the CU result. And then the H would be in this simple example, the U1 electromagnetic. One thing where we get first information is, of course, if you're going to parameterize this field, this form here, anybody who has been working calibration theory knows this type of structures. You get the gauge interactions, Lagrangian, so you have the field sigma here. It's nothing else than the bion matrix over F, which is the so-called decay constant. You have the vacuum structure, which is in this case is a very simple vector with an F having been here. You get the kinetic term of this. We can expand this in terms of the fields. And what this model predicts is that you get deviations of the Higgs coupling with the vector bosons here, and that's the Higgs squared with the 2 vector bosons here, parameterized in this ratio C, which is the Wef squared divided by this decay constant squared. Precision data tells us, because we know part of the couplings here, the vector boson combinations here, as I've shown before, that this F should be at least 1 TeV, maybe somewhat higher.
I have a question. In the QCD case, you have the 3 boson boson has a negative tendency, right?
Yes.
And in this case, the boson boson, the would be boson boson eaten by 3 gauge boson, WG and Higgs are in the same, they are all the same multiple Goldstone boson. So I wonder, in this case, do you have a correct parity for?
Yes, that has correct parity. Can I write here? So we have the pi doublet. So we did SU2 left times the SU2 right here. This gets broken to the SU2 diagonal. And then this decomposes on this with respect to a doublet. And here we have the triplet. This is CP even, so for the Higgs itself. But these components here become the longitudinal components of the vector bosons. And they have precisely this negative parity to which you are referring. So the triplet has this negative parity as required, and this singlet has the positive one as we need for the standard one. Did I understand your question correctly, or did I misunderstand your question?
Maybe we can talk later.
Okay. No, it's really this decomposition of the pi doublet in terms of the SU2 diagonal, which gives the singlet and the triplet.
Yeah, in that case, the axial current is broken, so the corresponding boson is pseudoscalar. And in your case now, SO5 is broken to SO4. So it's the broken current is just. So it's not axial, right?
So it's not really, so there's one combination, the triplet, which has CP odd, as you need to have to be able to get the longitudinal components of the vector bosons. But it turns out the singlet here that CP even, as we need for the Higgs boson. Roughly speaking, you can say that the SO4 gets broken to SO3. That's this part here. And this is a singlet with respect to the SO3, and therefore it is CP even. So here we have coming back the precision from the precision data bound, a lower bound on the F. And of course, the more precise we get and the closer we will get to the standard model prediction, the larger these values would have to be, and then we again have the question, how natural is the theory itself? So that's an important quantity to look at. Another point, of course, is fermion masses and couplings, because the Higgs transforms now as a nonlinear representation of this global group G. Therefore, you can couple it directly to a linear realization or linear vector like elementary fermions, as you would like to have it. This brings in the idea of spatial compositeness, where you have a combination of the fermions of the standard model, which are denoted by small q, L, and left to right here. This contains the SU2 doublet. This contains the right-handed upquark. Notation looks somewhat weird, but I simply implement this in the SO4 structure. You have here the doublet and here the singlet part. And then you have composite objects where you have this constituent hyperfermions giving you bound states like up and down quark proton, gives proton and neutrons. You get this type of structure here. Then you can write products of those psi with the QL. If you do this more formal, you see that the Goldstone matrix in between. You have to expand the Goldstone matrix, and with this way you get the coupling to the Higgs boson. And then you have essentially this coupling to the Higgs boson as a coupling to the capital psi q. So there are two versions, one for capital Q, then with prime numbers which give the small q here. But these are really two different objects, mixing either with the left or with the right-handed quarks. And in this way you can get the fermion couplings to the Higgs boson. If there's only one generation of this psi here, then one can always say, okay, this three generation of the standard model, still we have SU3 flavor symmetry. So we can always take a combination coupling to the psi here, and this is the one which will contain the third generation, which gives us the largest Yukawa couplings. In this way, we can really explain the largest of the top Yukawa couplings compared to the other Yukawa couplings, which are generated in a different way. I will come to this very briefly towards the end of my talk when I summarize the results, what the operator would look like. what we just in advance, an important quantity will be the mass of those guys here, because the couple will roughly scale like 1 over the mass of these guys squared. So just to summarize things, as a potential solution to this hierarchy or fine-tuning problem is we start with a freely interacting theory at the high scale. We confine at some scale lambda, which we now call lambda hypercube, which would be corresponding to lambda QCB. I don't know how this dot come here. Sorry, that's a small mistake. Should be, of course, the same F as here without the dot. Only 6 nodes large on the screen. This is the decay constant. So this is the scale, roughly speaking, where the bound state forms. This is the scale F, the decay constant. Then we need for sure the Higgs as a pseudo-number Goldstone boson. And one thing we already have to explain to some extent is why is this H smaller than the F. Partial compositeness gives you a theoretical tool to do that. And what you would then expect is that, of course, we have here additional resonances. It could be fermions. I marked those in red because I will discuss them in some more detail later on. There could be spin 1 resonances, spin 3.5, and so forth with higher masses. As you observe in QCP with the baryons, vector bosons, and so forth. Then, beside the Higgs, you usually expect additional BNGPs. In the minimal model, they have exactly 4 degrees of freedom, as we need for the Higgs field itself. But if you have some larger symmetry group, there will be more BNGPs. And of course, we are interested in finding those guys here. There will be, of course, additional deviations from the Higgs couplings, which are model dependent. I will not discuss those here, but I simply will take from the minimum modulus bound of 1 TeV for the F, even though we know, strictly speaking, we have not evaluated this for all the models.
Is that 1 TeV is coming from a lab or the LHC?
It's from the LHC data. No, it's from the precision measurement at lab, to be more precise, which gives us the this deviation. So it's the T and the S parameter.
What about in the higher LHC? In the future Higgs coupling measurements?
Then this will be competitive. So currently, yes, we are close to the precision that we would get from the precision data, if I recall correctly, but we are not yet there. But I would guess already towards the end of run 3, we should be competitive. But it's naive theory guess, not foreseeing any potential problems that we might have at the future measurements. So please take it with a grain of salt, my statement.
Okay.
So, and then of course people said, okay, this first of all, this minimal model, you can't really embed in a 4-dimensional UV completion. You can do this within a 5-dimensional one, this works. So people ask, can we do something in 4 dimensions? And they had here some lists of requirements. I will go through them. I simply want to show they exist, because I see I'm already somewhat slower than I expected. The important thing is that if you have these requirements which you need from a theory point of view, like no elementary scalars, as you would like to have, simple color group, if possible. We need the Higgs, we need top partners for the composite Higgs models. And then what you find that all of these models that I will just present very briefly, a list, have additional BNGPs. One can classify the next 2 minimal cosets, which are appear at equal footing, so to speak, which are the SU4 or SB4. This has 5 BNGPs, same like beside the Higgs. The SU5 or SO5, which I will concentrate on, this has 14 in total. And then you have the SU4 squared over the SU4, which has 15 BNGPs. We do not consider this only for the electrolytic sector, but also for the strong sector. And then what you see is that those are the 3 minimal realizations that you can get. Then you will get actually color-charged BNGPs. I'll give you this particular example of SU6 over SO6, where you have 14 BNGPs. Here you would have 20, and in this case, you would have 8. And they would, in all of cases, you would have a color octet within this SU3 color octet within this number of BNGPs. Here would have in addition triplets, and here would have an additional sextet. So this is this list of so-called minimum models people came up, going back to the work by Gabriele Ferretti. I don't want to go through this list, it's simply to show that various realizations, and of course, the question is how do you test these models at the LHC? And what we want to do is, and that's why I present first the simplified model, is look into features which are common to all models. We have certain PNGPs, we know there are doublets inside these courses, we know there are triplets inside these courses, we know there are singlets inside these courses. So we study those generically at the collider. I will not really focus on the colored ones. I will present some numbers, explain where they come from, but because of time, I cannot go to cover the sector as well. And then I will mainly focus on this model here called M5 because it shows the richer structure, showing the key elements one should look at. So, but let me just first start with the so-called simplified model. So the idea is let's take out the features which are common to all of the models, look at the processes that we have, and see which information does LHC give us more or less in a model independent way. And then in the second step, I will show you that in a concrete model, the bounds can actually be much stronger and how to combine the simplified model bounds to get really in a model the corresponding bounds. So there will be a couple of scalars. There's a capital S for scalar, it's color neutral. If there's a pi for this color, for this PNGP, then it has color charge. It will be within a SO3 color representation, it can also have electric charge. For the color neutral ones, I will go up to electric charge 2, because that's the maximum that we have in the cosets. And all of these states they usually come as SU4 representations, and that's the minimum set that we want to have within the electroweak sector. In addition, there could be also a -4 third charge fermion, but that's very similar because we do not distinguish between the W plus and W minus in the experiment to the 5/3 charge guy. So we did not include this here in particular. So we used MudCraft to generate events. We used various recast tools like meta-analysis, checkmate, contour, and then we check for each data point which tool gives us the best constraint. That's the principal approach that we have here. The caveat here, one should say, of course, we rely on the analysis implemented in each of the tools. And these are, of course, not all LHC analysis, so it's only a subset. And each of these tools has a different subset of LHC analysis. They're partially overlapping, but they are partially as a different analysis. That's the reason we really have to check in every case for the different analysis tool that we use, which gives us the stronger point. So the electroweak PNGPs, let's start with those because they're closest in mass to the Higgs, that's what we expect. We have various processes as we can have combination of double charge with single charge with neutral, pair production of either singly, doubly, or neutral guys here. We will consider two limiting scenarios because the way you make this partial compositeness, you can have it either those coupled to quarks. Then we have this thermophilic scenario because we expect the couplings are proportional to the corresponding fermion masses. And top and bottom, your color couplings are the largest one. Or we say there are no couplings to the quarks of these additional PNGPs. Then we would have so-called anomaly-induced couplings because we would still have a global anomaly like we have in the standard model, giving the couplings of the neutral pion to 2 photons. So these couplings here of the very same type as the pion coupling. And then we would have for the double charge, for example, if you have the pair production here for W boson final state as already shown by Han before. Okay, there's a similar one, but Han shows actually this one here, as on this side, the double charge with a set of photons as mediator. Looking into the case, you see the lists that we have. So either we have here many vector bosons, particular importance later on will be those containing the photons, or we have here the quarks. Of course, the top quark is the most interesting guy, but as the B quarks, if you can do the B decking properly. Then if you apply these results or this procedure set before, I show you here one particular result, namely this doubly charged pair production. What you see here, the full lines are the different channels that we considered here. And this is the bound that one gets using those tools on production cross-section times the corresponding ratio. Because we did not want to assume there's only one channel possible, but copy principle more channels, but then you would have the task to combine different channels, to which I will come later on. What this also shows is results from a dedicated atlas search, which this started quite some time ago in the context of snow mass. Atlas produced intermediate some results which were interesting for us, showing that, of course, if you have a very specific search for these final states, of course, you can do better. So whenever I show bounds, they are very conservative in the sense it's really existing on existing data, but it could be even better, this you should keep in mind, if you would go for a very specific search as done by the Atlas collaboration in this case. So here, the improvement would be roughly speaking, 1.5 to 2. Here, it could even be a factor of 3 to 4 in the bounds. Then, of course, you would do the calculation in a particular model and see where do you cross these lines here, as I will show later on for the SO5 or SO5 course. Just one word. What the Atlas did here, they looked into a CSO2 model, which contains a SO2 triplet. And this production cross-section is precisely the one that we get for this eta 5 multiplet I will present later on. So there's a direct connection to our model, which also shows what we do here is also valid for other models. So this goes back and forth. What I show here are now the results for the best channels that we have found. V means in particular Manuel and Leonard. And you see here go now the bounds down to all a few femtoquants, depending on the mass. So we expect from those channels that they will give the largest bound, provided, of course, that the corresponding branches are sizable in the concrete model. But you should note here, all the states here contain at least 2 photons. We'll also look into other channels, which I will not show for this electrolytic stuff. Let me just show you very briefly the results you get for the hadronic channels. There you see that the bounds, roughly speaking, are in order to orders of magnitude worse compared to the best case that we had for the photon final states. Nevertheless, even though I will not show it just to invert, if one combines the different channels for the model I will present later on, you can get bounds order 450, 500 GeV. The second thing I was interested in has been the vector-like quarks. Those are searched for by the LHC collaborations. We usually look into standard signatures which contain standard model fermions and standard model vector bosons. But of course, if you have an extended PGB sector, you have many more potential final states depending on the mass hierarchy. Then things could look much more complicated. Okay, these final states are already very busy. But here, it's even busier. And what we were interested in, what can be said about those final states to be as model dependent, as at least model dependent as possible. Of course, making the assumption that you have the state here, that you have a particular final state is already a model. So that's why I said before, these are simplified models. And that's the most vicious plot that you will see here in this talk. That's really the summary that we made for snow mass, combining all the information that we had. One word of caution right in advance, what you see here, this is the vector boson mass plane, this is the mass scale of the BNGBs. And for this find here is 95% confidence level of the tools that could be used at this time, so on the analysis. And they were mainly based on 36 inverse femtobarn. At this time, there were not higher luminosities available within those tools, although the data existed. The details you can find in our snowpass report here. So the full lines here are the current results that we have. You see here on the different channels here, I don't want to go too much into detail, that we have bounds, which can go down to 600 GeV. And here we go up to 1.2 TeV. I should add, so I forgot to mention this before. Using these channels here, get bounds of the order 1.3 to 1.4 TeV. So what this shows you, if you have these more complicated situations, the bound can be weakened considerably. It can even go down in some cases to a few hundred GeV. So roughly speaking, half of the bounds within the standard channels. What you see here are single searches for this standard model part here, which shows, I said here, it's even close to 1.6. Sorry that this bar is not so good visible here. What we also did then was to ask ourselves, okay, what can be done if we really have LHC at the end with 3 inverse autobahn? What would be the potential reach? And those are the lines that you see here, which are dashed. Colors correspond to those full lines here. There's some modeling included here. So, for example, if you take this particular state here, which is the first one, we have a top quark and a singlet decaying into 2 photons. There comes some kink in those lines here, which we understand because experimentalists gave us different efficiencies for the different regions here, which of course can be improved. So eventually this kink here will vanish. I think there will be some smooth line here. So what you should take from here, current bounds are ordered depending on the final state. If it is more complicated situations, between, let's say, 700 to 1.2 TeV. Taking the full luminosity, I would guess, if you add a factor squared of 2, this would be drastically bound with the current luminosity. It can go up to order 1.7, maybe 1.8 once we're at the end of the LHC, if such a more complicated model is realized in nature. It will turn out later on, in particular models, you can even get stronger bonds. And let me come to this particular model right now. So this was model M5, which has a hypercolor group of SB4. The global group would be SU5 plus SU6, so this will be the electroweak factor. This will be the strong factor, and this gets broken to SO5 in the electroweak sector, SP6 in the strong sector. If we look into the BNGBs, it's just an accident in both case sectors. You have 14 BNGBs, simply because of the groups chosen. If there were, for example, SO6, there would be 20 instead of the 40. In terms of quantum numbers, if you go in the electroweak sector for SU2 left, that's SU2R, you have the singlet, you have the bi-doublet, which contains the Higgs boson, then you have a bi-triplet. In the singlet, which we denote by eta, we're not interested in it here because this doesn't have any electroweak gauge couplings. It would only have electroweak gauge coupling while mixing with the other states if some of the other guys would get a wave. Then we have this bi-triplet here. It's broken into a singlet of the diagonal subgroup here. So the same decomposition as I did here, into a triplet and into a 5-plet. And this 5-plet, as I said before, has the same production cross-section apart from the neutral component as this triplet had for the Atlas investigation.
I'm sorry, the eta is a singlet?
So this one is a singlet with respect to the diagonal subgroup, but it still has couplings to the vector bosons.
What about the other eta?
This one is a complete gauge singlet. So this is this singlet here of the SU2 left and SU2R. You gauge the SU2 left, but it's a singlet with respect to the SU2 left. Hypercharge for these guys comes from the third component of the SU2R. As there's a singlet, so it's a complete gauge singlet. But it still could have couplings induced by the anomaly. But this I cannot exclude. And I think that's what you investigated in another work, if I recall correctly.
The related state.
Yeah.
So this is a state which comes purely out of the electroweak sector. So it has Western written terms only with electroweak gauge bosons. So it's basically very hard to even produce this part.
What about mixing with
It would only mix with the Higgs if the particle is getting partial, or this can only happen via the potential in the web. So if you have a misaligned web, then you could get a mixing angle, but typically this particle is not getting any mixing.
That's actually a good point. So we always assume that the only particle getting a web is the Higgs boson itself, and not of the other neutral ones.
I was wondering which one is the dark matter candidates in this.
Here, I will come to this point. It's not in the scalar sector, actually, in this particular model.
Okay.
So very briefly, the color charge formula for a pair of color triplets. For those of you who are familiar with supersymmetry, it will turn out this is very much like a right-handed scalar top. And then we have a color octet here. Now, the fermionic states, we would have to look into an SO5 times SP6 representation, so it would be 5 with respect to SO5, 6 with respect to SP6. And if we decompose this combination here into the standard model quantum numbers, then you would find those pairs here that I've shown before for the color triplets. It turns out there's also, this would be the third combination of the color triplet. We would have here a color octet, which however is a color doublet, sorry, an SO2 doublet. So it contains not only a neutral color octet, but an electrically charged color octet fermion, which would be quite unusual. And they would have a color octet which is singlet with respect to the electric gauge group. You would also have a singlet with respect to the SP6. This comes like a doublet with respect to SO2 left. And here we have a complete gauge singlet. The letters G tilde, H tilde, and B tilde are not chosen by accident, but really on purpose, because the properties concerning gauge quantum numbers are similar like the ones to the corresponding supersymmetric particles of the gluon, the E meson, and the Higgs in this MSSM. But please, there are no relations between couplings like in supersymmetry, except, of course, they need to have the propagation directions. But this also tells us that we can use partially as a SUSY information or SUSY searches to constrain the sector. In particular, it turns out that this model, if you really look at the level of the hyperfermions, contains as an accidental symmetry, as a global symmetry baryon number. And this in the end implies that one of the either one of the fermions here or the pi3 has to be stable. Of course, on colossal reasons, we don't want to have a charged dark matter candidate, so it should have charge 2/3 in the end. Therefore, what the neutral one should be is dark matter candidates either the E tilde or the H tilde here. So for the following, I will make the assumption that this pseudo-lump Goldstone boson is somewhat heavier than the lightest of this fermion. It's somewhat unusual, but because this is an SO3 singlet, this is an SO3 triplet, you have some model freedom to do that. But of course, one can ask the question what happens if one includes those guys here to be lighter and those here, then you need to add by hand additional terms violating either baryon number or lepton number. Let me first discuss briefly the electroweak BNGBs. So what I assume is that all custodial multiplets, so all members of the 5-plet have the same mass, all members of the triplet have the same mass, so we don't have any mass splitting. There's no mixing between, for example, the neutral BNGBs nor between the single charged ones. All of those have couplings to the anomaly, but for this eta 03 here, as one can show, so this guy cannot decay in the fermiophobic case into electric gauge bosons directly. Here we need to have 3-body decays via either here the charged guy here or the neutral guy here. So we would have 3-body decays containing W's and gamma and Z, or 3 of the neutral guys here. Now, if there's some mass difference between these multiplets, so between, for example, the triplet and the 5-plet, you would have the additional decay channels via either on or off shell vector bosons, which has some impact on the bounds and will then, because this will depend on the mass hierarchy. So let's use the information we've got from the simplified models before. The dashed line here is the bound that we have. The full line is the production cross section for this channel within this model. And clearly, the crossing point within the bound, which here would be order 350 GeV. This is actually, I chose this example because it's the most important one in this context. You can take the other ones here, which have come out of this list here, and you see here the crossing points are always below. But of course, they all contain here photons, at least 2. And the question is, do they populate the same signal regions the experiment looked at? Because if they populate the same signal region, actually you can combine the different channels very easily. And indeed, what we did as a cross-check, or what has been done as a cross-check first is, let's take the full model, do the simulation, plug in the data, in the tools, and then you see that the bound is much higher. But this is simply an artifact that we should really to get the full bound combine all these regions here. And if you do this in a very naive way, you will get the blue line here. We have the section of this blue line here with different curves here, given this ellipse here, and you see order of magnitude here really coincides. So this really tells you, if you have simplified models, you apply this to more complex models, have a careful look what are different channels, different bounds, check whether you can combine the signal regions, combine those properly, and then you get the actual bound in your model in a very easy way. Of course, what I showed here was simply taking only the 5-plet. That's a simple example. You can do the very same thing now, adding the triplet and the singlet. I simply show the final result here. So this is the cross section you get combining all the different channels. This is the bound that you get from the different channels, and you see here, roughly speaking, I have here a bound of order 630 GeV.
What is the plus minus?
Sorry. This assumes here we have the singlet mass, the 5-plet mass, and triplet mass. We only have a small mass splitting here, order few GeV. The reason being twofold. We do not really expect all of the masses to be equal, so we expect to have at least a small mass splitting. And the second, but it's a very technical thing. If one goes back to this graphs here, for exactly equal masses, and assuming that the constant f goes to very large values, this decay mode would vanish. It's a very artificial situation, I know. But simply to avoid any coincidences, because this would imply that the ether string would be stable.
All the scalar in the same multiplet has the same mass, but different multiplet has a slightly different mass.
Exactly. That's the meaning of this slide before.
But if their mass is really in the regime of degenerate, then those particles can be long-lived.
No. No. They have small decay widths, so they could have large lifetimes. That's possible. Okay, there is a limit, of course. All these couplings are scale like 1 over f. So if you make this f sufficiently they're not reduced at scale at 1 over f. Actually, the width is like 1 over f squared. Therefore, of course, if you make the f large enough, you can get in the end for very large f's long-lived particles. If in the order of a few TeV, there's still too short-lived and decay inside the detector.
Oh, there is no long-lived particle signatures in this real equation.
Not for decay constant in the range of a few TeV. Okay, if we go here really to very tiny mass split, let's say order electron volt, then I guess the ether split could be long-lived. But this would, as I said, this would be really fine-tuned. But of course, this bound does depend on the hierarchy, and it just shows you one example where the bound is even somewhat larger, close to 700, or slightly above 700. If the triplet is lighter than the 5-plet, and the 5-plet is lighter than the singlet, which is somewhat counterintuitive, but we cannot exclude it on logical grounds. This simply shows you this model for this coset, but that's in this model class. Because what I show here doesn't really depend on the M5 model, but on all these models in this list I showed at the very beginning, containing this coset. So that's really, this sense, independent of this particular model, but belongs to a model class. So what you should take here, in this model here, taking existing analysis, we get bounds of the order few hundred, let's say 600 to 700 GeV. Just in words, because I don't have time to go also the plots. If you were the case into quarks, it would be order 450 to 500 GeV. So somewhat lower, but not much lower. What I also want to discuss briefly are the hyperbaryons, because we have seen their color octets, their color singlets included, beside the usual color triplets. And one can now say, okay, what we know, taking QCD as an analogon, those particles belonging to the same multiplet should have the same mass. So we expect for this 14-plet here, we have a complete the same mass where these colored objects are reside, and for the singlets, color singlets, we should have approximately the same mass. This splitting here is partially due to standard model gauge interactions. This splitting here is due to the mixing of the top quark with the top partners. And as I said here, this would be due to the electrolytic interactions, small splitting. When I say small, if these guys have masses of 1 TeV, the splitting are typically in the order of a few GeV or below. So really, we speak about splitting here in the per mil to percent range, here somewhat larger. But they have overall the same mass here. Therefore, what we'll assume in the following, for example, we'll take the octets here that they are really mass degenerate, because for the collider energy, whether we have a particle of 1000 or 1010 GeV, there's no difference. Now, of course, one has to compare the cross-section of the color triplets with the color octets. That's what you see in the plot here. It's well known, color octets have larger cross-sections than color triplets. And this is just to give you an idea, it's an order of magnitude. And that's the reason why the following will focus here on the color octets. Because we know the color triplets should be the same ballpark, so if we get a mass bound on the color octets, automatically get a mass bound on the color triplets. Yes?
So this color octet, are they composite?
They're composite, yes.
So is there any reason why they are significantly lighter than the composite fermion?
No. This color octet, that's what this as a composite fermion.
So I'm talking about the T3, T2, T1.
These ones here?
Yeah.
They're all composite fermions.
So my question is why this color octet is lighter than.
Okay. The idea is if we would neglect standard model gauge interactions and mixing of the top particles with the top quark, we should have all the same mass denoted by M40. Now, the gauge interactions give us some positive mass shift. And as this is a color LHC2 singlet and we have a SU2 doublet, we have here the case of the small g, only the SU3 interactions. Here we have in addition the SU2 interactions, so we have this mass splitting here. You would say, of course, the color triplets have a smaller SU3 part compared to the color octets. That's the reason why this X503 is lighter than the color octets. I think that's what you would naively expect. But those guys here, they mix with the standard model quarks. And this mixing induces a slight positive mass shift. That's the reason why we expect that those guys here are somewhat heavier than these color octets. But we talk here about a percent effect compared to the mass. So it's not really that they are heavier by orders, by let's say 100 or 200 GeV, but we speak here of mass difference of the order of 10, 20 GeV, maybe 30 GeV. Not much more. Maybe I should put some relative scaling numbers here in future. But does this answer your question?
Yeah.
So, as I said before, we'll assume that the fermions within this multiplet have about the same mass. Either we have this M14 or the M1. This can be different. This sets the relative overall mass scales between the color charged object and the color neutral objects. I will assume that the V delta is stable, motivated by this accidental binary symmetry that we have if you look really at the level of these fundamental fermions forming the bound states. And what I know, of course, is from the LHC that we have the color octets giving the larger cross sections. And because this guy here is stable and it's lighter, what we will assume, we will have, like in supersymmetry, events with missing energy. Which implies we can really reuse SUSY searches to constrain this model here, despite the fact it's composite. So the possible decay modes are this octet decays into top quark and this color triplet BNGPs. This is why I said before, this looks like a right-handed scalar top quark. It has precisely the same quantum numbers. Or it can decay into this baryon, singlet fermion, and the pi8. And similarly, for the Dirac, two EMOs under quotes, you would have the corresponding decay modes in pi3 or pi8. Now, we have seen before there's a small mass splitting between This xenon-like states is H plus H0. If this bracket is Venus, so the symptoms is lighter. Then you would have the case like you would have compass spectral supersymmetry, which are Chino-neutralino sector, into a pion and the lighter state here. But of course, due to the small mass splitting, these bands are very soft. So essentially, all of these guys here, the H plus, the H0, will contribute to missing energy. Because these jets come from the pions, they are below the thresholds to be identified as a jet. Except in the unlikely case that a very strong boost. Of course, the pion 3 will also decay. This will be decaying into top, and this let's call it Beano-like state. If in case that the pion 3, I assume it to be heavier than the Beano-like state, if it were to be lighter, that's a case we could not discover cover here. They would have to introduce either lepton number validating couplings leading to the case like to top quark and neutrino, or bottom and tau, or you would have bio number validating materials. You cannot have both at the same time because then you would get problems with proton decay.
You are saying that the B tilde is stable.
Yes.
Why is it stable?
If one really looks into the level of the UV completion, one looks in the directions, one sees that the complete model has a by accident bio number conserved. And
But the B tilde has a made of three constant part.
yes,
Three.
but there are three, but there are two different kinds.
So it's similar to the usual proton lifetime longevity.
Yes. But this disability is really due to the assumption that I assume that this P pi 3 is higher than the B tilde. If we were around the B tilde would decay into the pi 3 and top quark. And the pi 8, we take in the following either that it can decay into two gluons or in the top anti-top pair. In principle, as it decays into the lighter quarks are possible, but we're simply interested either to top jets or to light jets. So those jets, even though they're deeper, they differ from the gluon jets, they're essentially covered by the glue jet here. So for this rough analysis that we do here, the detail between a charm quark and the gluon jet is not of importance. We know from SUSY searchers that this stop tilde for the pi 3 should have a mass above 1.3 TeV, so we'll assume later on 1.4 TeV. And then in a paper that Giacomo did together with Thomas and others, we know that the Cal octet should have a mass of at least 1.1 TeV. So as this we assume as lower bounds on this color inches.
Bounds are higher because this is color.
Yes.
A quick question about the pi 8 octet, which indicates the blue. Is it possible that it can form blue ball, which mixes with the Higgs, and then decay to some different planet states?
That's a good question. I never thought about it.
I'm not interested in the glue ball, but since they can decay to like the glue ball is CP even, so you can mix with Higgs.
I think in the case of the pi 8, this is relatively short-lived. So this probably doesn't have enough time to form blue balls.
Yep.
Oh, okay.
But pi 3s,
They would have to form bonds with the quarks, yes.
yes.
But they would form either neutral and charged one. That's a problem with cosmology.
Okay.
So this would not work for it would work from the collider aspect, but not in terms of cosmology.
So for the pi 8, the decays are basically prompt.
Oh, okay.
And you get bounds from two pairs of two jets signatures, and this has been looked for. The color triplet scalars, with them it's not obvious how they decay if they are lightest. Here the assumption is that B is lighter, so they decay fluid. But if the mass hierarchy would be the other way around, and the barrier number is conserved, then they would be strictly stable.
Yes.
This would lead to problems. because they would form bound states and you would bounce from this.
Yeah. So actually, you can have them stable, but then you would have masses of at least 16 or 20 TeV. I don't recall now the numbers. So beyond any possible LHC you reach, and even a 100 TeV collider cannot search for the spark. Yeah. And those would be the lightest states. So how do I produce those guys now, the color octets? So of course you would have light supersymmetry for those who are familiar with supersymmetry pair of Wiener production decaying into what would be the scalar top device 3 in the top quark, and this guy would decay further in anti-top and speed tilde. So we would have here 4 top quarks and missing energy as a signature. The very same is true here. It would take the charged one if this pi 3 decays into top and the Wiener tilde here. As well as here for the pi 3 here, we have the neutral color octet Dirac fermion, as a here would get 4 top quarks in the end plus missing energy. Sorry, here would have 2 bottom quarks, 2 top quarks and missing energy. Slightly incorrect. So this would be somewhat different. Here it would have the case now, beside going to pi 3, I have the case into the pi 8 here. So you would have here either 2 top quarks from the pi 8 or 2 gluon jets, missing energy. Now if one assumes that one of the decays, either top quark or gluon, is dominating, then in the case of the dominating top quarks, the final state would be very similar to the one here. Of course, kinematics is different, but it turns out that the differences in kinematic are not too essential. So the bounds that we'll see will be relatively similar in both cases. And what you see also here are the additional decay modes of the color Dirac particles. They always contain, and this actually should be a capital H, sorry for that, which indicates into this missing energy plus the soft stuff, but the soft stuff you do not register. So essentially, you have the very same signatures like for this color Twino-like state. Now, this essentially means if I take supersymmetry, you roughly speaking multiply the SUSY cross-section by a factor of 5, take the bounds of the Twino, you get roughly speaking the bounds on this model. This is what gives you a first order of magnitude what you have to expect. So this simply a brief summary, you have 4 jets missing BT. And the 4 jets can be all of them can be 4 top quarks. You can be 3 top quarks and 1 jet. Then it goes down to 4 jets only without the top quark jet. Of course, additional soft pions we don't count. And then what we did was that we recasted SUSY searches. Here it turned out that my analysis 5 gave the strongest bounds. And for the cross section, we took the one for the blue inner for SUSY from this page here and multiplied this simply with a factor of 2 if you considered a Dirac neutral state, an octet, or a charge. Because UCD does not care about electric charge. And well, just slept already over time. If I assume now 100% as a limiting case into the pi 3 here, what you see here is the octet mass. I should say when I write here Q8. So let me go back here. If you write Q8, it's really the sum of all of these color octets here. That's what the meaning of the Q8 is. So simply what's important is the color octet property. The electric charge, whether it's Majorana Dirac, is not very important at this stage. So we have here the octet fermion mass, you have here the singlet scalar fermion mass, which would be the spino-like mass state. That's the case where 3 binding case would be important, which we did not cover. So the lines would cross this slightly here. And we see here, if the single fermion is significantly lighter than the color octet, we get bounds here up to, roughly speaking, 2.7 TeV. If you compare this to the bounds say for the color triplets, they even at the end of LC would only expect 1.8. And we know already in this model we expect the color triplets to be somewhat heavier. So this immediately tells us that the color triplets should be in these mass configurations be heavier than 2.7 TeV. So in that sense, it's no surprise that the color triplet searches didn't find anything. Of course, if you go to smaller mass differences, as it's well known from SUSY searches, the bounds get weaker. You can also have here, what we did here, we took difference between the color of the fermion mass and the pi3 to be constant 200 GeV. Of course, we can also fix the mass of the pi3. This gives us a simply different kinematical configurations. And what you also see here is that the bound is roughly speaking, but case of 2.6 TeV, the 1 sigma will be slightly above, so the gray is 1 sigma, this is 2 sigma. We did not go with the singlet mass above 1.2 TeV because the pi3 should decay to the singlet plus the top. Because otherwise we would have to consider 3 by the case of the top quarks, which we did not do in simulation. But this can be slightly extended, and I do not expect the bound will get some slight bending, but not much. So what you should take here as main message, the bound is roughly speaking 2.6, 2.7 TeV, depending on the kinematic configurations. It can be somewhat lower if the mass difference between the color singlet and the color octet fermion gets small. Now, if you look into the case, the other imaging case, if only the case of this color octets into the color octet PNGBs, then one has to look into the case that you have either 2 gluons for the P8 or into 2 top quarks. We also did different combinations. I still show the limiting cases to give you the order of magnitude, and the other cases are somewhat in between. That's what we find here. We get close to 2.75 TeV if we have the case with 2 gluons, simply because we have more phase space available. Here for the top quark it's slightly less, but again, order 2.7. This is 2.65 TeV. And again, we have the feature for smaller mass differences, the bounds get somewhat weaker. So the main upshot is it's the same order as before. So whether it's intermediate case via pi3 or pi8, it's not very, very important. Clearly, in the end, once we know a spectrum and once we have measurements, this will be important, but not for this type of searches. Now, as I argued before, we have now bounds of 2.7 TeV on the color octets. We know that the color tripters should be somewhat heavier. So one can show us that really this coupling, the top cover coupling, would scale roughly speaking like 1 over m top squared. That's what I get from a under quotes naive analysis. It's not really that naive. In the composite Higgs models, if I were to use gauge gravity duality to do similar estimates, you also would find that the heavier the sky is, the smaller is corresponding with the top cover coupling, using completely different method. So there's of course the question, how do I get really a large top cover coupling? I have no answer to this yet, but this of course might also be a way to rule out certain model classes. So just to be very brief in my conclusions, we know composite Higgs models are a viable class of models avoiding the fine-tuning problem, but we also see, if you look into the details, that we are pushing this further, the boundaries. What we also have seen in this talk we should take here, so take a home message, is realistic models usually have more PNGBs than simply the Higgs boson. It can even be color singlets, it can be color charged. If they're color charged, we have at least color octets that's independent of the coset.